Okay, let us continue our lecture on sequences and series. What we learned so far? We learned about sequences. Now we moved on to series. Our goal is to analyze a series. Well, recall that we defined a sequence by listing the terms of that sequence. We say that, hey, suppose you have a sequence, f of n is equal to a sub n. So we list the terms of the sequence, a sub 1, comma, a sub 2, comma, a sub 3, and so on. What we do, we take the limit of this function. If the limit exists, if it's a unique number, we say that, hey, we have a convergent sequence. And that's it for us. Very well. Now we add the terms of a sequence and we create something new, which we call a series. By adding the terms of a sequence, by adding the terms, we introduce a new object, which we call a series. A sub 1 plus a sub 2 plus a sub 3 plus. Remember that here we say we use a Greek letter sigma to show that we have summation over the terms a sub n starts from 1, goes to infinity. This is an infinite series. Our goal is to analyze a series. Okay, to analyze a series, we need to define something new that we call the partial sum. Definition. Perfect. Suppose we have a series. This series is denoted by the sum a sub n starts from 1, goes to infinity, and you all know that you need to add the terms of this series. A sub 1 plus a sub 2 plus a sub 3, a sub 4, and the rest. So that's how we define a series. The end partial sum of the series is defined this way. The end partial sum. So it means that we are adding some terms and we stop at the end term. It's denoted by the sum a sub I. I starts from 1 and it stops at n. The partial sum, the end partial sum. So it means that we have to stop at some term. What term? A sub n, the end term. So you have a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus the rest of the terms, and we stop at a sub n. This is called the end partial sum. So now we're going to use the end partial sum to talk about the convergence and divergence of series with infinite terms. We say that if the sequence S sub n is a convergent sequence, is convergent, then its limit is equal to a number, a unique number like S. This is a number, a unique number. It's not infinity, it's just a fixed number and it is unique. If the limit is equal to S, it means that if the sequence S sub n, this is S sub n. What is S sub n? S sub n is the nth partial sum. 1 to n is convergent, then we say that our original series, infinite series, is convergent. And we say that the sum an, n starts from 1 to infinity, is convergent. So this is a series, and then if you give different values to n, you define a sequence. For example, S sub 1 is equal to A sub 1. S sub 2 is A sub 1 plus A sub 2. So this is the first term of the series, and then you define it as a sequence by assigning numbers to these n values. So this is the first term of the sequence. This is the second term of the sequence. By adding them together, you get the nth partial sum, S sub 3, A sub 1, A sub 2, A sub 3, and S sub n is A sub 1, A sub 2, A sub n. So this is your sequence, the nth term of the sequence. The nth term of the sequence. Here we go. Very well. We're going to define a geometric series. Geometric series is important for us. Why is that? Because we're going to eventually use geometric series and some other series to help us analyze more complicated series.